Hi everyone! Today we're going to tackle 9.4 part 3. We're going to do the integral test and the p-series test. So first with the integral test, it says if f is decreasing, continuous, and positive when x is greater than or equal to 1, and you think of your sequence a sub n as a function f of x, then your series, the sum from 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx either both converge or they both diverge. So let's think about this. We studied improper integrals like this, the integral from 1 to infinity of f of x dx, back in section 8.3 part 1. That was the first one we did. We had to rewrite it as a limit, and then we evaluated that limit as b approached infinity. So basically what the integral test is saying is that as long as these initial conditions are satisfied, decreasing, continuous, and positive, you have a little acronym here, dogs, cuss, and prison, to help you remember the D, C, and P. And again, we're only looking when x is greater than or equal to 1. Then if I can evaluate that integral, then I know what the series is going to do. The first note, that does not mean that the series converges to the value of the definite integral. So just because the definite integral converges to 5 does not mean that the series is also going to converge to 5, only that it is going to converge. And note 2, the function need only be decreasing when x is greater than k for some k greater than or equal to 1. So we're really looking at whatever this start value is here and here. So if that n value started at 3, well then I'm looking at the integral from 3 to infinity. We're going to ignore the second piece. I'm just going to draw a line here. We're going to ignore this for right now, and we're going to come back to that later on after the AP exam because it's not on the AP exam, so we're going to bypass it for now. All right, so let's take a look at some examples. I'm going to make this a little bit bigger. So I want to determine whether the series from n equals 1 to infinity of n over n squared plus 1 is going to converge or diverge. So first off, what you need to do, remember your nth term test. In your mind, you don't have to write this, but you're always thinking about, is the limit as n approaches infinity of your a sub n equal to 0? Because if this is not true, you get to stop and you get to say that it diverges. But this one is true. This is true because that n squared is going to win compared to the n, and therefore that limit will be equal to 0. So now I'm thinking it's not geometric. That was my other series that I had learned. So I'm on to the integral test. So the integral test says as long as my a sub n, which is n over n squared plus 1, is decreasing, check, positive when from 1 to infinity, and continuous. I should have done it in order. Check, that thing is continuous. Then I can use the integral test. So I'm going to evaluate the integral from 1 to infinity of x over x squared plus 1 dx. And whatever this does, my series should do the same thing. So first, to evaluate this, I've got to rewrite it as a limit. So I'll rewrite it as the limit as b approaches infinity of the integral from 1 to b of x over x squared plus 1 dx. Next, I have to actually evaluate that antiderivative, and I'm going to come down here to do that and do an aside because I'm going to have to use a u sub. So I'm going to let u be equal to x squared plus 1, and du is then 2x dx. I'm going to pull that 2 to the other side, giving me 1/2 du equals x dx. So now when I rewrite my integral, I'll have the integral of 1/2 du all over a u. So if you can want to take a closer look at that, I actually want the highlighter. All of this is my u. And then this x dx here is getting replaced with 1/2 du. So then you can see that. All right, so now my 1/2 is just a constant. I'm going to pull it out front, and now I have to do the antiderivative of 1 over u, which I know is the natural log of the absolute value of u plus c. And then replacing my u back in as x squared plus 1, I have my antiderivative here. So now back to the improper integral. I have the limit as b approaches infinity. My antiderivative is 1/2 natural log of the absolute value of x squared plus 1, and I'll be evaluating that from 1 to b. And now fundamental theorem of calculus, I'll be plugging in the b, and then I'll subtract, plugging in my lower limit of integration, and there I get a 2. So as b approaches infinity, this natural log of b squared plus 1 also goes to infinity, meaning this integral is going to diverge to infinity. Therefore, I need some more space. So here's all of my work right here. So therefore, the integral from 1 to infinity of x over x squared plus 1 dx diverges. And I have my supporting work. So my final, therefore, I know the sum from n equals 1 to infinity of n over n squared plus 1 diverges by the integral test. So just a little recap. To use the integral test, I need to first make sure that my sequence is decreasing, continuous, and positive from, in this case, 1 to infinity. Once I make that connection, I can move on and evaluate my improper integral. Make sure you show all of your work. This aside may not have been necessary for you. It was for me to find that antiderivative and make sure all of my work is in place. I found that my improper integral diverged. Therefore, I know that the corresponding series is also going to diverge by the integral test. Let's take a look at another example. So here I have the series from n equals 1 to infinity of 1 over n squared plus 1. So I'm again going to do my first gut check and just make sure the limit as n approaches infinity of 1 over n squared plus 1 is indeed equal to 0. It does, just to make sure that the nth term test for divergence doesn't apply. So now what I can do, I need to take a look and say, is this series a sub n equals 1 over n squared plus 1? Is it decreasing from 1 to infinity? It is. Is it continuous? It is. And is it always positive? It sure is. So now I can go on to find the integral from 1 to infinity of 1 over n squared plus 1. Oh, I could keep it with n and then say dn, but you guys are probably more comfortable thinking about this as a function. So let's change it to x squared dx. All right, so off the gate, I would probably go ahead and rewrite this as the limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1 dx. And then comes the hard part. What I would need to do is I need to come to the side and evaluate this integral right here. And I can do that. If you notice, this is going to be equal to tan inverse of x plus c. So you can proceed that way. Or maybe you look at this and you forgot that tan inverse. So what I want to do is I want to review a comparison test just because I see an opportunity to review a comparison test. And I'm going to do a direct comparison test. So let's say we don't want to actually just evaluate this. What we want to do is use a comparison. So I have 1 over x squared plus 1, and I know that that will always be less than 1 over x squared for all x from 1 to infinity, and that's the limits of integration. So here's my comparison. Remember, in this direction, if this one converges, then the smaller one will also converge. And remember our comparison tests? We like to use those whenever a p integral is involved. So what I need to do now is I need to evaluate the integral from 1 to infinity of 1 over x squared dx and see what that does. Well, this I recognize is a p integral. So this right here will converge by p integral. Not only do I know that it converges, I also know that it converges to 1 over p minus 1. So it'll converge to just a 1. If you want to review your p integral rule here, for the integral from 1 to infinity of 1 over x to the p dx, this will converge when p is greater than 1 to 1 over p minus 1. And then it's going to diverge when p is less than or equal to 1. You also had another p integral that worked from 0 to 1, but we'll have an opportunity to review that another time. We'll wait till it actually applies. All right, now, so let's think of what you've got here. Since I know that the integral from 1 to infinity of 1 over x squared dx will converge by p integral, I can therefore say that the integral from 1 to infinity of 1 over x squared plus 1 dx will converge by the direct comparison test, DCT. And therefore, let me scroll up a little bit. I know that the sum from n equals 1 to infinity of 1 over n squared plus 1 will converge by the integral test. As you're determining if these series are going to converge or diverge, notice just the burden of proof that you have to follow. It's really important that you show all of your work and that it's in a logical order. Now there's a reason I wanted to use this p integral test here, and I wanted to review this old p integral rule because the next test we're going to learn about is going to be a fan favorite. It is called the p-series test, and it is an extension of this integral test. So let's think about a p-series. So a p-series is going to be a sum from n equals 1 to infinity of 1 over n raised to that p. And so you can see that you'll have 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 da, 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 plus 1 over n to the p, plus da 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 da. So think about your rule, again, that we just had up here. We said that if I have an integral from 1 to infinity of 1 over x to the p dx, that it converged when p was greater than 1, and it basically diverged the rest of the time when p was less than or equal to 1. So think about your x's now as your n, because we're not really looking about functions, we're in series notation with a sequence a sub n as your rule. So if p is equal to 1 here, meaning you have the sum from n equals 1 to infinity of 1 over n, your series is going to diverge. And this is basically because of the integral test, but we say by the p-series test. So we have p integrals and we have p-series, and they behave essentially the same way. If your p is less than 1, then the series will diverge as well by p-series test. And then if p is greater than 1, the series will converge by the p-series test. Note, we cannot find the sum of the p-series. Up here with my integral, I knew that it converged to 1 over p minus 1. So the integral is going to converge to that. However, for a p-series, I do not know what it's going to converge to. I can't find its sum. And this is more often the case than not. All right, so we have some examples. We got 4 left to wrap this up, but I think they're going to go pretty quick. what I wanted to do here was make sure that you recognized p-series when they applied, because they're really easy as long as you recognize them. So here in the first one, I have the sum from n equals 1 to infinity of 1 over n times the square root of n. So we just need to recognize that this is the sum from n equals 1 to infinity of 1 over n to the 3 halves. So you'll see here, this is going to be a p-series with your p equal to 3 halves. And since your p is greater than 1, I know that the p-series here is going to converge. And you just say converge by p-series because p is greater than 1. And that's all. Let's take a look at the next one. So I have the sum from n equals 1 to infinity of n over the square root of n. So if I clean up this is raised to the first, and I could rewrite this as n to the 1/2. You'll have the sum from n equals 1 to infinity of just n to the 1/2, or the square root of n. Putting that in my p-series form, you could also write that as 1 over n to the negative 1/2 if you wanted to. So you can see your p-series here with p equal to negative 1/2, and therefore your series will diverge by p-series. You could also use an nth term test here. So once you have this cleaned up right here, your a sub n is equal to the square root of n. So you just have, if I take the limit as n approaches infinity of the square root of n, you just get infinity, and that is not equal to 0. Therefore, you could say the series diverges by the nth term test as well, if you wanted to. All right, 2 more. All right, so the next one, we've switched it up a little bit. When I clean this one up, I have the sum from n equals 1 to infinity of 1 over n to the 1/2. So here I have a p-value of 1/2. And that is going to be less than 1. Therefore, the series will diverge by p-series, because that p-value is less than 1. All right, and then my last one. I had the sum from n equals 1 to infinity of, that is a big number. Let's see. I'm going to have to put in some commas here. So 999,999,999, all over n raised to the 1 point, lots of zeros, 1. So important thing just to remember is you can pull out any constant, no matter how large it is. So I've got 999,999,999, sum from n equals 1 to infinity of 1 over n raised to the 1 point. 1, 2, 3, 4, 5, 6. Man, I need to count. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. 1. And now I can really just look at this right here. So this is a p-series where my p is equal to this 1 point, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then a 1. And that is greater than 1. Therefore, I know my series here is going to converge by p-series. Note, I have no idea what it's going to converge to. The p integral that's associated, if I were to consider this p integral, I could tell you what that converges to. This will converge to 1 over the 1.01 minus 1, so it'll converge to that. But I do not know what the series is going to converge to. It's very important. So just to recap, today in this lesson, we had 2 tests. We had the integral test and the p-series test, which are very related. And we got to review a good bit here. We got to review old comparison test, a direct comparison test, which was good. We got to review a U-sum. We got to review the p-integral rule. So that's all good stuff to review.